at where you need to be, but keep you a little dangerous at the same time. So I'm thinking in 2 weeks, and then after that, I'm thinking a presentation from you guys. By next week, you really, if you guys want to know where you should be, by next week you should have your parts in-house, and you should start building, and you should have a majority of it built if you don't already have it built. Because if you have it built now, that software is going to be that much easier. Even with the idea of using the simulator. Yeah, you guys don't care about my JPL talk, I'm sure. You don't want to do JPL talk. So I gave them. I went to JPL last summer to do a talk for them on bulk engagement systems. So we are in 4751. Serial manipulators. And this is a 2D lecture. And I believe we are in. Oops, sorry, that one. How many people are graduating this semester? How many F's do I need to get on? Keep you all here.
Is that the F's who don't agree to do the masters?
What?
F's to those who don't agree to do the masters?
Exactly. Come back for master's degree, I'll pass you. Absolutely. Maybe. I don't want to cost you. No, master's cheap. Actually, it's cheaper than undergraduate. Yeah, because you only take 6 units at a time. We're only expecting you guys to take 6 units full time status. Yeah, it's more work.
Is it 30 units?
It's usually a master's degree is 30 units. Okay. Yeah. So I highly recommend all of you guys to do it. I really do. It's gotten to the point where you need a master's degree to do design work for the most part.
You better right after or after 3 years?
That's depends on really your single project and the job market. They paid for my entire graduate degree. My company only paid for my undergrad, or paid for my master's and my PhD. They don't always pay for PhDs. They like me. I made them a lot of money, just put it that way. All right, so we were, I believe, here, right? On kind of got through the overview or this part. So we are. Yeah. I'm not sure why I have an extra slide. Okay, no, we did. And so the idea, we've gone through this notion of kinematics, forward kinematics, inverse kinematics for cylindrical, Cartesian, and spherical, right? So, okay, that's pretty easy. And then we got into this idea of this articulated arm. So in this articulated arm, I could literally say, I've got a joint that's from this base that's going to spin like this, right? And like this, and like this, and like these could both. I mean, theoretically, I could have these two be two separate articulating joints if I wanted to, right? I could do this. There's a lot of degrees of freedom in this robot. And it could be cylindrical, it could be spherical, or some combination thereof, right? So the question is how do we succinctly, how do we concisely describe the parameters relative to one another for the inverse kinematics? Because as we saw, if I said that this was the orientation, that I'm going to move this one and then this one, it would be a planar robot. But if I said that that one could move, now all of a sudden, it's no longer moving in that same plane, is it? So I've had to somehow capture what that twist was, and maybe it's a fixed twist. Maybe it's not even a joint that's allowed to move. Maybe it's just rotated. So now this one moves this way, and this one moves this way. So how do I describe that twist from this joint to this joint? It's no, if I said it's not a controllable joint, it's just fixed. I mounted the motor 90 degrees. Remember when we were building the arm in Coppelia and we rotated that motor? This has got that joint motor rotated by 90 degrees. And that reminds me, I'll you guys a video to post. Okay. If I don't do it, someone feel free to send me a note, say I forgot to give you guys that video. But that's what's in there, right? So how do we describe that? How do we express the relationship of that twist? It's not a joint that's moving, per se. How do we make the difference between this axis rotating and maybe this does rotate that way? I mean, there could be that relationship. So how do we do that in a repeated manner? That's where the Dennett-Hartenberg representations come into play. And so when we look at this, so what is the Dennett-Hartenberg representation? So the DH parameter representation, I'm missing this. Oh, man. There. Okay. So it's a simple method, and I say simple in quotes because I think it's simple, but it could be way more complex. But it is a method. I'm going to still say a simple method. Once you get the hang of it, you'll say simple as well. It's a way to model how robot links and joints. And when I say joints, it could be, it doesn't matter if the joint is prismatic or revolute. So regardless of configuration to one another. That's what Dennett-Hartenberg is striving to achieve. That's a very big statement with a lot of dependencies behind it. So, well, we understand what those letters and what those words on that page mean. Putting that into practice is obviously going to be a bigger picture. But what we can do is use it to describe the transform. And this is the key part, is we're going to use it to describe the transform in any coordinates already developed. When we say that, that has implications right here. That it can support any configuration of robot arm. Whether it be RRR, so revolute, prismatic, and this is the same as a Cartesian. RPR, PRP, RRR, whatever, PPPR, it doesn't matter. You can get the point, right? It makes no difference. Spherical, cylindrical, SCARA, Cartesian, in general, any articulated arm. The DH parameters will allow the ability to describe arm motion we'll be using it to do force analysis. Etc. We can also use it to describe general joint motion and movement. In fact, it's interesting. if you're a kinesiology major, if you go to grad school in kinesiology, you'll learn DH parameters. But if you're an engineering and undergraduate, you learn DH parameters. So you can go into grad school in kinesiology right now.
You're saying joint motor in humans?
Joint motion in humans.
Oh, no.
Joint motion. So those are pretty big asks, right? What we just said. So the question now is, how do we establish these DH parameters? I'm going to go through a little bit of a cookbook method, and we'll talk about it, and it'll still be completely foreign to you. Trust me, that's okay. How many have read up on the reading that I asked you to read on DH parameters? Yeah, you're going to consider yourself at a disadvantage right now if you didn't read it. You really needed to have read that. So we will be doing a quiz coming up on this material, so look for that. And it might be on stuff we haven't had that's in the reading. So yes, definitely want to get that. So first thing we're going to do for DH parameters for the description of an arm, first thing we're going to do is we're going to assign a reference frame to each joint. We're going to assign a coordinate system, so to speak, for each joint. And we're going to do it in a special way. Okay. But the first thing to do, in fact, even on your exam, I'm going to give you guys, first thing I'm going to say is assign a coordinate system to each joint. How you put those coordinate systems together, it could be arbitrary, but if we do it smartly, we can save ourselves an enormous amount of headache. Because we can arbitrarily put it however we want, just within some constraints. Then what we're going to do is use a general procedure to create a transform from one joint, from joint J, to the next joint, J plus 1. So we're going to assign a reference frame, and then we have a general procedure which allows us to connect one joint to the next. So we have this joint here, and I have this joint here. And there could be a twist in that joint relationship. There could be a link in that joint relationship. We want to capture that characteristic. We want to capture if this, which way we're rotating. If we're going to rotate about this joint, or this one's going to be this joint. Or maybe there's a prismatic joint. Maybe it's going to move along, so it has a linear motion. We want to be able to capture all of that. So that's our objective. And so what we're going to do is we're going to chain one joint to the next in a serial fashion. This is why this is called serial kinematics. That's the whole idea here. So we are chaining these transforms, and this is where we get the word serial kinematics, or the expression serial kinematics. We're going to do that from each joint, from one to the other. And by doing so, we create the robot's overall transform. So if I have a transform which describes relationships from this joint to this joint, transform from this joint to this joint to this joint, so on and so on, from the base to the tip, I can multiply each one of these transforms together and thereby have a transform that represents the entire arm. So I can describe through all these motions, or all these joints, that spot that the robot's currently touching. And if I want to apply a certain set of forward kinematics, I can move it from this point say down to picking up something over here. I can say I want to move it to over here. I can apply another set of motions to make it go over there. I can also arrive at what that transform looks like by by solving for the inverse kinematics. That is, I can solve this, given the 2 points, I have this point and this point. Remember, the inverse kinematics solves that transform matrix, how to get there. And if I do that, I can decompose each one of these guys from that one overall matrix, figure out then the next successive transforms themselves. So we have to ask ourselves, what in fact is a robotic joint? What is a robotic joint? And a robot joint or joints may be prismatic or revolute. So prismatic, if you recall, that's linear, and revolute is the rotation. But we don't call them those, we call it prismatic and revolute. Moreover, each joint, and this is a constraint we place for the DH parameters, are considered to only have, this is key, 1 degree of freedom. So what we see on this sheet right here, on this page, in the chapters 3 and 4 in your textbook, we won't be covering them, but those are going to, instead of be doing serial kinematics, those are parallel kinematics. That's the chapter 4. Chapter 5 deals with spherical joints, which is the combination of more than one motion that it can move. So we're going to constrain ourselves in a serial robot. So we're not doing parallel, but we're doing link to link to link to link to link. And we're only going to allow these joints to have 1 degree of freedom. That makes life a little easier. Once you know this, you can easily go on and read the other 2 chapters, but we're going to go ahead and move on from there. Between any one of these 2 joints, so for example, I have a joint here and a joint here. So let's call this, say, joint 0, joint 1, joint 2. Between joint 1 and joint 2, I have a link. I have a joint, I have a link. Everybody with me on that? So definition of terms. So between each joint is a link. What's between each joint? A link. What kind of joints can we have? Revolute.
Prismatic.
Couple of observations. A common normal. What is a common normal? We're going to define that for you guys right now. The common normal is the shortest. In fact, let's just think about what this is. A normal is a perpendicular, right? Perpendicular between things that are something in common, right? So the shortest distance between any 2 mutually perpendicular lines. Of the z-axis of 2 neighboring joints. I'll show you what that looks like in a diagram, slide 9. You can see what's coming up. the common normal, the normal, so that's kind of the plural, the common normal, are not necessarily intersection or collinear. And what this implies is that the origins of two successive frames may not be at the same location. And that makes sense, right? The frame for this joint, is not the same location as the frame for that joint. It could be though. Wait, what? What it means is we'll find out that when I do a rotation, does it matter if I say it's rotating here or if it's rotating here? Doesn't matter. But this guy clearly is not rotating there, right? So the way I have this planar and this planar here, they're not rotating. They can't rotate. But if this has a rotation joint here, I could say it's actually rotating at that point and rotating at that point, not necessarily down here. That translation doesn't have a whole lot of meaning to what I'm going to do for the rotation. Okay. We got that so far?
In that case, would there still be a link between the two guys?
Not necessarily. We may not have to worry about it. We can ignore it. Yeah. Yeah, exactly. But there's one right there. No, not necessarily. It depends on how you define it. So let's talk about, this is the diagram that gets everybody confused. We're going to spend some time on it. Oh boy. This is why I used to draw it as part of the lecture. I don't do that anymore. I don't know if it's good or bad to not be drawing it. In some ways, it did help because I think as I was writing it or constructing it, I walked through it. So by all means, if you want to draw it, please do so. What we have here is this is joint N. Here we are. Let's just say that joint N is down here. And that joint is revolute. Right here. So it's doing this. Okay. N plus 1 is going to be right here. And it's rotating like this. N plus 2, or make that joint. I'm going to do this. I could have said this is N plus 2, and this is N plus 3. Between each joint, joint N and joint N plus 1, I'm going to have link N. So I have a joint connecting a joint, and notice the diagram shows here, this is that perpendicular, or this line is here is perpendicular right here. Okay. Totally different axis. This is a right angle, but this is a right angle. This is that mutual perpendicular. Perpendicular to both z-axes. It's the shortest line, isn't it? That is going to be what we call our link length. And we'll write this down in another slide. The link is not the traversal length. It is the shortest distance between my two z-axes. For joint N, I'm going to have a theta N that I'm rotating. Now, what I'm describing is the Niku notation. If you were to look at Craig, the subscripts are different. In Craig, this would be n, and this would be n plus 1. This would be Zn plus 1. In NICU, we're looking forward as our n. And we look back and look forward. In Craig, we're continually looking forward. It's the same thing at the end of the day, and you'll get really comfortable with it. But if you look at the Craig book, which is probably one of the other most popular robotics books that exists, Craig is going to use a slightly different notation. And I have lectured both of them in the past. I started with just Craig and then went to NICU. I don't know which is better. A couple of years ago, I just switched to strictly NICU and explained to you guys the differences. I want you guys to be aware of the differences of what's used in literature. Because there's a difference. There's a difference. It's a difference. Neither one's wrong, neither one's right. It's simply a matter of perspective and where you came from and where you're going to when we describe the serial connectivity from joint to joint to joint. Okay, everybody with me on that? So we notice we have this z-axis for J, for joint N, and it's about Zn minus 1. I am about theta n. So that joint right here has a motion. This is isolated. It's this guy right here. It's turning this guy right here. My z-axis is coming up. Everybody see that? Zn minus 1, my theta n axis. This is joint n. I have theta n. To get to joint n plus 1, I have this common normal between my two z-axes. This is the link. Between the two z-axes is the link. This is the joint displacement, theta right here. It rotates about the z-axis. In fact, every joint motion is about the z-axis or along the z-axis. Now, to get to this orientation, so z is pointing this way, now I have a z pointing that way. So I have a rotation about some axes, in this case it's going to be my x-axis. It's rotated about my x, and there's my x. Here's my z. I'm going to rotate about my x-axis to get to the new rotation. I'm going to rotate about the x-axis by alpha. That's alpha n. Wake up. Here we go. Again, my mutual perpendicular. A is the distance between my two z's. So I have frame n minus 1, frame n. All motion is about my z-axis, or taking that common perpendicular, the common right there, if I displaced along the z, that displacement is known as d. So my displacement is along z is a d. My joint displacement, if I had a prismatic that was moving inward and outward, that's going to be by an amount, d. So my joint can move about z along z. The axis that we control is the z-axis. That is the axis of motion. The axis of link to link is going to be along this guy here, which we're going to make our two x-axes co-aligned. We make them co-aligned by a twist alpha. So twisting of the alpha is a way of aligning my x-axes so that my z's are pointing in the right direction. In other words, this is rotating right here. Here's my joints. My z is going to be coming up here. Now all of a sudden, this guy, I'm going to build the arm as we go. It's now rotating this way. It's no longer rotating this way, right? It's rotating this way. So where's my new z-axis? It's coming through here, right? My z-axis is literally through the joint right here. So z went from here to here, following the right-hand rule, x cross y is z. What is doing that rotation is alpha. It's the twist in the joint. So this has a 90-degree twist going from the vertical to make it into this direction. So that my z, this is going to be that's my joint, which means I have to rotate about z, right? If I'm going to rotate about z, that means z has to be this direction, right? How did I get it in this direction? I rotated alpha by 90 degrees. I also have this AN that's this length right here. If I had a displacement inward and outward that was doing this, then that would be my z-axis inward and outward. So that's the idea of having this z. So motions are about z. The physical structure are about x. Professor, but what about y? Can't I do y? Yes, but no. We get to y, and we'll see an example. I'll give you guys this in the book. By rotating an additional 90 degrees about the x, and that is 90 degrees. Remember, I'm rotating about z, right? If I'm going z and I want to add 90 degrees, what does x become? Y. Right, so here's my z. If I rotate this guy by 90 degrees, okay, guaranteed, what does my x become? Y. So how do I make a rotate about y? Theta plus 90. Cool, huh? So wait a minute. Let's talk about this. I'm rotating about z. I know how to do descriptions of rotate about z, don't I? I know how to do that transform. Do I know how to do a rotate about x? Sure. We memorize those. We learn those. What's my rotate about? What's my transform to rotate about z? Upper left corner is what? Cosine theta. And then cosine theta, 0 dx. Next one.
Cosine
theta, cosine theta,
0,
Py. Next one.
0, 0, 1.
PV. 0, 0, 0, 1.
There you go. That's the rotation matrix.
The transfer.
That's, wake up. It's because I don't have it plugged in. It doesn't like this power supply going through here. I know it didn't have a battery. I charged it last night. At least I thought I charged it last night. Yeah, I've got plenty of charge. There we go. Okay. Where are we? What I should do is just plug in a different. Well, it's waking back up again. Plug in.
There.
Let's just do higher for this guy that's I'm just gonna plug it in right here. Oh. All right, so I can rotate. If I take a transform of this rotation of theta, I can do that, right? And instead of saying cosine 90, my variable, my joint variable of how much I'm rotating becomes theta, cosine theta. Now, alpha, that may be fixed, and generally is fixed. So there's one example where we actually have a D that is fixed. And I'll get to that in a minute. So if I have a fixed rotation, I'm rotating about this, now I want to rotate about this, I had to have a twist of 90 degrees, right? So I multiply by, what's the x transform? 1 px 0 cosine I'll assume you got your minus signs correct. I don't know. Make sure you don't. Okay, so there's my py. The alpha is not going to be alpha. It's going to be whatever it is. Generally, we try to keep it 90 degrees to make life easy. So then we just have a bunch of ones and zeros. Okay, that's to be honest with you. So if I'm 90 degrees, cosine 0 is going to be 1. So I stick a 1 in there. So if cosine alpha is 90 degrees, it's a 1. Easy, right? Sine 90, 0. So it's 9 ones and zeros. Back to like binary almost. Okay. And if I have to rotate about the y, instead of it being cosine theta, or the sine theta, it's theta plus 90. Problem solved. Now, I said sometimes we actually move along z. If I have a offset, if this joint and this joint are not right here, but there's like maybe this link actually had some spacing between it, then d would have a fixed value. It's no longer the joint variable of transversal, it's actually some offset. Sometimes that gets students confused, and sometimes I might have that traversal, and I really do have a theta as a fixed value, because I did rotate about, I have an angular offset now about that rotational joint. Okay? So it's not always this or that. Sometimes we might see both. Sometimes students don't realize that and don't feel bad. When I was an undergrad student taking this class, I was like, oh, it's always a 0. No, it's not. Or oh, it's always this or it's always that. No, it's not. It could be both. I want to talk about the instructor because he just didn't explain that. But anyways, nonetheless. Then we rinse and repeat as we go from this joint to this joint. Okay. So now we go to joint n plus 2. Again, NICU's notation has us the n minus 1 from that joint. So this is always the z minus 1. And this is where Craig and NICU differ. Okay. Just kind of giving you the heads up. Same concept, same process. It's just how you identify going forward or going backwards. So there's always a link between the two. Well, there doesn't have to be. What if this had a rotation? What if I said, you know what? I don't really care about this part. It's not doing anything for me. It's going to rotate. And then I'm going to have an alpha twist right in it. I could put that together, believe it or not. Okay? So those actually can combine. We'll see an example. We're going to do a lot of homework examples on this one, this whole concept. But this is serial robotics. All the stuff we've been doing up to this point has been describing the concepts of forward kinematics, the concepts of inverse kinematics, the concepts of a transform. Why do we need to have transforms? What is a rotation? Why does a rotation work? Why is rotation nothing more than the projection? All that stuff has really been a tool to help us identify these diagrams. Everybody with me?
I have a question.
Yes, sir.
When we're talking about alpha and
Yep.
alpha n specifically, that's the angle between the two z-axes?
Yes, it is.
Okay.
Actually, it is. It's exactly what we're showing. Okay, everybody with me on that? Like I said, sometimes I used to draw these. I don't know if it's better to have it pre-drawn for you, trying to understand my chicken scratch, or if it's better just to see it already done. You guys tell me, what would you prefer?
Already done.
Okay, fair enough. And this is the diagram from the book as well. So if you were thinking it's the same, it's the same. So notice that we have. You guys can see the pointer? Yeah. So notice that over on this one, the mutual perpendicular is right here, right? Shortest distance between two z's. That's what you want to think of. So here's the z, and here's the next z. There's an alpha twist about the x. It's kind of hard to see that in here. You just have to kind of like, okay, I get it. I'll be honest with you, it's not as 100%. One of these days, I'll actually create a 3D model that allows you to play with this and stick it in here. I haven't done that yet. That's on my to-do list. Usually, I always get usurped by any number of other things I have to do. So one day when I have absolutely nothing to do in my life, I'll probably do that. The likelihood of that happening is probably 0 to none. It'd be nice, so I got a lot of other things that are have tos as opposed to nices. There's also more have to nices than nice to have tos. Okay, so, let's talk about this next one. So, what can we say about this? Z-axis from the joint frame. All joints are rotated or translated. So these are the conventions, as you might want to call it. In movement, about or along the z-axis. As you were seeing from the diagram, you can still see from the diagram that you have it below. It's the same one, if you're curious. I just shrunk it down. If the joints are revolute, the rotation is using the right-hand rule. This is Z, so it's going to be using X cross Y, so it's doing this. I.e. counterclockwise. Right? Was that counterclockwise? X cross Y. Funny story about that. I'll tell you in a second. If the joints are prismatic, the elongation is along the z-axis. And the frames at an S, are oriented such that the motion of the joint align in this manner. The motion about Z is defined by theta. The motion along Z is defined by D. So we've talked about theta, we've talked about D. These are the official things. So this is the Z-axis. Everybody good on that? Make sure you're all written down. In contrast, we have the X frame. So the X frame from J to J plus 1 is used to align. So we're using the X axis to align and translate from one joint to the next. So the X axis is to align the frame from J to J plus 1. We want to use the rotation about, we use A because we're using N, O, and A, but we're going to call it X. And translation. So rotation about and translation along. So again, this is using the other format, but it's also known as X. To me, I'll always think of it as X. I have a hard time with the NOA approach. Just because I prefer XYZ. The rotation about A is defined by alpha, and we call this the link twist. Whereas the translation along the A-axis, this is defined by A itself. That's why I don't like using that NOA, because it gets confusing. Is known as the length. This length is the common normal between the two joints. Okay. I don't care how curvy and wiggly or anything else we have about that. We're not doing path length. We're doing the shortest length distance between 2 points length. Same with by way of the way the crow flies, right? That's what we're talking about. That's the shortest distance between the two z's, i.e. the common normal.
Oh, is that the AN at the bottom there, between joint 1 and joint 2?
Yes, that would be this guy right here.
Yeah.
I think we talked about it before you walked in. So we have A, alpha, D, theta. That's it. We have twist, length, then we have displacements of theta and displacements of D. So if we're looking at it from one joint to the next, how do we relate these two together, right? So we have the picture that we have right here. This is our starting point. And how do we relate the two joints, Jn to say Jn plus 1? So that's what we want to do. So we're starting with this one. We really want to go to the next. We were starting at this joint. We want to get to that one. So how do we use these ANs and DN plus 1s and beta N's and X and Y's and Z's and everything like that to do this operation, to do this relationship? And so what we're going to do is we're going to rotate our Zn axis an angle of theta n plus 1, such that xn and xn plus 1 are parallel. So you want to go from n to n plus 1, so we're going to rotate about that Zn by some theta, and this is where it should be theta n plus 1. This is where it gets kind of confusing. So the next theta, so to speak, so that the xn, where I'm at, and where I'm going, are parallel. So far, so good. Then, now that we've done that, we're going to translate along our Zn the amount of Dn plus 1, so that xn and xn plus 1 are collinear. So we're going to translate along Zn axis And it says angle in the source note, it should say an amount of dn plus 1 such that xn and xn plus 1 are collinear.
We just want to align our origins or our dates.
Basically, that's what we're doing. So that's what we're doing right here. Then what we're going to do is we're going to translate along the xn an amount of an plus 1 so the word collinear, now we're going to bring them together. We're going to move it from here. We're going to translate along that line now to collinear. Or they're now actually on top of one another. And then last but not least, we rotate by an amount alpha. So we rotate our Zn about the xn plus 1 axis by an angle alpha n plus 1 to align the AZ and AZ plus 1 axes.
Do you mean to put Z in, or what is AZ?
That's the x-axis, but it's really the about the
Oh,
A
okay.
frame. It's the new Z. So if I look at this in totality, we go through each one of these steps. So we do a rotate, translate, rotate, etc. on each one of these individually, right? So we rotate an alpha, we translate a D, we translate an A, we rotate, I'm sorry, we said that over. We rotate a theta, we translate a D, we rotate an alpha, we translate a link.
Can we write the order?
They're in the slides. The slide order is the
Three
order.
steps, it's A, B, F.
So that's what we see right here. Each one of these is those orders. Here's our starting point, and we do each one of these. This is just all of them together. So far, so good. So we're just trying to get everything like, okay, how much should we what do we need to do to get from here to here? That's really what we're saying. We're constructing a transform. Right? Isn't that what we just did? We talked about the displacement and the rotations to get from one place to the other between the two axes, x and z. And again, in y, it just goes along for the ride with a theta plus 90. So if we need to rotate about y, it's theta plus 90. So, when we're looking to create a general transform, there's really 4 baby transforms or subtransforms that we've chained together. Rotating about z, by theta n plus 1. Translate along z by dn plus. Now again, quite often, if there's no offset between the joint and the next joint, which is very similar in robotics, which is what we have right here, we might oftentimes say that, okay, that rotation to this rotation is in and of the same, it's the same spot, so D is basically a 0. So a lot of times we'll say it's a 0. Not always, but quite often. So that means that D is not really there. It's there, but a lot of times the examples it doesn't show up because it's just, we're assuming them to be right on top of each other. But there could be a small D. Rotate, that's the 0. Then we had an alpha of 90. So now that my Z is now going to go inward and outward like this to me. And so after we've translated, we are going to translate along our x-axis, well, again, A. I'm just going to call it x in quotes. By an plus 1. And they're going to rotate about that x by an alpha n plus 1. And if we look at what we just said, here's what we have. So here's rotate about x, right? This is our rotation matrix without any translation, just pure rotation of z of n plus 1. We're going to translate from n to n plus 1, joint n to joint n plus 1. Sometimes you might see them on the same side. Sometimes authors might put them diagonal to one another. Sometimes you might see this one here and this one down here. Depends on the style of the author. All of them are something.
Which notation do you prefer?
I'm flexible on here. Just be consistent. So then we're going to create this transform to go from just a general purpose transform. So the transform is this, but we're going to call it some A matrix. Rotate about z by theta. Translate along z by d. So notice, this is a rotation about z, right? Here's my matrix that does just translate along z. It's just going to be that value right there. That's our d value. I'm going to rotate about a. I'm sorry, I'm going to translate along a. So again, this goes to this guy down here. I'm going about x, so I'm going along x, so this is going to be that amount a. And then finally, I'm going to rotate about x by some alpha here. So everyone sees how we constructed this from these words. Trivial math. Remember, we developed these matrices from very simple linear systems theory, so it's trivial for that as well. Multiply them all together, we get this general purpose transform. So this is the transform that allows us to go from one joint to the next joint. And now what we do is we simply, based on the geometry, we put our numbers in. This could be 90 degrees, that could be 90 degrees, that could be 90, maybe there's 0, you know. We're going to have, this would be like a 1 or a 0, right? Maybe it's 180 degrees, maybe it's a 0, and that could be a 1 or a 0, right? Depending on if it's what that alpha angle is. If we're dealing with 90, 180s, 270s, and so on. If we're dealing with 45 degrees, that's 0.707 all day long. Question?
So now that we've I guess it's like a translate, like we force joint 1 to be in line with joint 2. Like how does that help us? Like, what do we use?
Now, so that transform, now it says, if I want to go from this space to this space, it's related through that transform. If I want to go from this space to this space, it's related by a transform. If I want to go from this space to this space, it's related by a transform. Well, once I know my transforms, I can take this transform times this transform times this transform and know this space to this space simply based on the arm's geometry. My links, my twists, am I going to have a revolute joint of theta, or is it going to be a prismatic joint along D? And I can define all of that right here.
Oh, I see, it covers, it's a catch-all, it's like,
What's the general purpose transform?
no, because like when you said prismatic joint, I was like, oh, okay, because then that's why we have the translation.
There's our prismatic joint right down there, D sub n. And then I have all my thetas. And when you look at this, what we see here is notice that the x's, it's just a theta. If it's just the z's, it's just an alpha. Which is kind of weird when we think about it. But then you have these combined terms that are thetas and alphas. I also think it's interesting too here is then, remember, we're doing the projection, we're only rotating about D, right? We're only rotating about Z. That's our axis of, so what's going to get smaller? Is the Z ever going to get, the X and Y ever get smaller from a projection? No, but the X's and Y's will scale accordingly. So this is my X and Y, it's going to scale as a function of my rotation, which is exactly what we'd expect from a projection. Right? Remember we talked about the projection, this whole thing right here. So this is my Z-axis, my X and my Y's are getting smaller and bigger. That's exactly what this is showing us. That all makes sense now, yes?
A little bit.
Yes, a little bit.
Like I said, today is probably one of the bigger lectures that you have to be here for. This is a key lecture. Okay. So, example. All of that was very theoretical. A lot of fun. I love the theory. But what's theory if you can't use it? It's worthless. Right? What was the thing I said the other day, Maria, about
Math.
practical engineering? If it's not practical, then it's impractical. Why are we doing impractical engineering? Engineering
Yeah.
has to be practical, by definition.
There is no such a thing as
There's no such thing as impractical engineering. In other words, theory without application is irrelevant. Right? Companies don't hire you to do something that can't be done. Well, in theory it'll work. Well, in theory I'll pay you, but until you do something for me, I will do it. So we have this very simple planar revolute arm. And we can see it in this, if I configure it like this, I have a revolute, and a revolute. Okay, so they're all moving in the same plane that we see right here. It's a very planar arm. What's the very first step I said to do?
Rotating.
coordinates.
Assign
Assign the
Coordinates.
axes and coordinate systems. 100%. If you get this wrong, you're done for. Gotta get this first. Once you get this one right, it's a piece of cake. It falls right in the line. So what do we rotate about? What is our motion of rotation, our axis of motion?
Y is Z.
Z.
Z is always Z.
Right? So Z, notice we have Z0. So this is joint 1, joint 2, joint 3. This is where NICU gets you different from Craig. I'm going to be honest with you. If it's theta 1, that's Z0. Okay? Can you see the pointer?
Yes.
So there you go. So that means that has to be Z. Right? X cross Y is Z. So the question now is, where do I care where my X's go?
Yes.
Do I care? In this case, no, I don't. I really don't care. Later on, I will. But for right now, I don't really care. Because all I say is my X has to be X cross Y is Z. So here's my Z, which means my X is going to be right here. This is my universal coordinate system that I've drawn here as my reference. I can put it wherever I want. Okay. But the first thing we're going to do is we are going to assign axes such that my Z-axis for each joint aligns correctly. But again, as I say in the note, it's a planar arm, which means alpha is 0. The second task we have to do is to construct a table. In fact, I'm done here. Let me just go back to this other one real quick. My link, I've got right here. I've got right here. So here I defined my basic, or my basis right here, my base transform from on that joint. I didn't do it down here. I did it up here. I could have done it down here, but then I have to do a bunch of silliness. I don't want to do silliness. I'm going to keep it simple. So I'm going to actually do it from this point. So I'm going to have my A1 and my A2. I've got my theta 1 right here, my theta 2 right here, and its z-axis right there. It is easier when you draw these arms, to be honest with you though, if you draw it more like this, instead of putting that angle in there. It's the same thing, it doesn't matter, but it's just sometimes easier to visualize. So we see the Z's coming out, we see this guy coming out, and so on, and then we have the hand. Everybody see that? So if we have all of our information, we can actually build what's known as our DH table. And so what we're going to do is, I skipped the slide. We construct the table. Following the RR, maybe there's additional R, arm. Okay. So what we see here is our table. Construct the table for theta, D, A, and alpha. To go from 0 to 1, we have, so Z0 to Z1 is going to be a theta 1. Okay. Joint number 0 to 1 is a theta 1. We're going to assume there's no offsets between rotation and displacement. Is that fair? What that means is that there's, along that Z there's no offset, so we're going to put that as 0. To go from joint 0 to 1, we're going to have an A1. So we're going to go to that next member. This is where you get into the subject notation. So this is the 1 for Z1. Sometimes this gets students. It kind of gets me because I'm so used to the Craig notation. And I think, in my opinion, the Craig notation is more intuitive. But it's just a notation. To go from 0 to 1, is these are the joint 0 to joint 1s. We're going to have this link right here of A1. Is there any twist for my Z's to have different Z's? No. So that means our alphas are going to be 0. There's no link twist. To go from 1 to our hand, we have a rotation by theta 2. Again, we're going to assume that there's no offsets in our joints. We have a link from 1 to hand as being this A2 right here, and there's no twist. So the left column is the joint numbering. This is going to be their thetas, and these turn out to be, this is what we control. So this is what the motor rotates. When that motor turns, it's turning a theta. We structurally designed and built the arm with that twist, and we developed an alpha. We programmed alpha in by nuts and bolts. We programmed in the link length, A, by nuts and bolts. D might have an offset depending on how we built it, but if we don't have a prismatic joint, we can sometimes or generally assume it to be 0. It's a very small number quite often. Not always. so I don't always want to say that, but because there's no entries, we put them down as zeros. So now that we have our table, we can construct our matrix. So using the table,
I think you want one.
that's
That's
good one.
true.
Thank you, yes. I was just looking at it going, wait a minute, I think you probably wanted to do that. So using those tables, we see that now all of a sudden I can create this transform A1. So using the table, we construct the transform, the general transform, between each frame. Remember, each frame is a coordinate system for that given joint. Now, they're not the same because this is going to be, remember this refers to cosine theta 1. This is minus sine theta 1. And theta 1 and theta 2 are very independent joints. So they're going to have their own relation, right? They're going to, even though this is the same format, that number will be different than that number. So that's what we mean by cosine 2. So cosine 1, I mean, that's the shorthand notation by calling it just C1. Because we know we're rotating by theta. This becomes a value. That becomes just a value. It's just a number. And then we have our cosine and our sine right here. So from our general purpose table, go back to that real quick. Whoops. Going back to our general purpose table, we literally use this and fill it in. Cosine of alpha, that's going to be a 1. So that's going to be a 1. So those stay in there, right? This is going to be a 0, so they become 0. It kind of does the math for us, right? Just by plugging in if they're 90 degrees to one another. If alpha was a 45 degree, then all of a sudden that's a 0.707. So this is the general purpose transform, and we go through, we find our tables, and we construct our two transforms. To find our overall transform from our J0, this joint here, J1 I should say, to our hand, we multiply the two transforms together. So this becomes the general robot transform. What we can do here is we can do some identities of our sines and our cosines, and we can actually construct an even more simplified or more pretty. Is that a good answer? So we have cosine 1, 2, and this time we use the sine and the cosine identities, so we simply know that cosine 1, cosine 2 minus sine 1, sine 2 is equal to cosine of theta 1 plus theta 2, which we're going to call cosine 1, 2. And the sine cosine, so sine 1 cosine 2 plus cosine 1 sine 2 is going to be the double angle identity for sine of theta 1 and theta 2, which we're going to write as sine 1. And so when we do that, we can simplify this transform to be this transform that we see right here. And it's still very similar. The reason why is we have only rotations about the z-axis, which is why this looks like it's a z transform, or z transform, doesn't it? Because we're only rotating about z. If I was rotating about, if I had a 90-degree twist, then I would see that twist showing up in here. And it wouldn't necessarily be this simple. Is that fair?
Mm.
But because we're a planar robot, we don't see that. So we can write some of those simplifications. So cosine 1, cosine 2. If I had more than one, like maybe I had 4 joints, and they were all planar, I'd have cosine 1, 2, 3, 4 minus sine 1, 2, 3, 4, sine 1, 2, 3, 4, cosine 1, 2, 3, 4. These would all be zeros because it'd be planar about z. And then here I'd have a whole bunch of stuff here. So I won't get into that one. Does this make sense so far? Again, this is probably one of the biggest lectures that we're going to have in the first half of this semester. Today is what we built up to. We'll do examples on next week, and I'm going to give you guys some homework to start working on in NICU for more of this as we do more examples next week on this material. Sound good? I'm going to throw you guys a quiz. You can make sure you guys know what you're doing, so look for that over the next coming days.